So I'm going to launch into a new topic now, but it really relates to what I just showed you here in red. When we're working with an ionic compound like this in solution at the net ionic equation, you know how to work with that now. When it's in solution, an ionic compound, it's going to dissociate into its component ions. That's what we call an electrolyte. Electrolytes are simply compounds that when they're dissolved in aqueous solution, they dissociate further into their component ions. So these dissociate into component ions. The ions have a charge. They're either positively charged cations or negatively charged anions. And that's why we call these electrolytes, because you have charges now in solution. So sodium chloride is our favorite example of an electrolyte. As you know, it's you put sodium chloride in aqueous solution. So here's solid sodium chloride. We put that in water, and it dissociates into sodium ions and chloride ions, and we write that in aqueous solution. If we take magnesium sulfate, that's another ionic compound, that will dissociate into magnesium 2+ ions and sulfate 2- ions. You remember, of course, that this is a polyatomic ion. Now, polyatomic ions, when they're in aqueous solution, they don't dissociate further into sulfide ions and oxide ions. No, because they are a covalently bonded molecule. They just happen to have a net positive or net negative charge due to the number of electrons relative to the number of total protons in that molecule, right? It's a molecular ion, but these don't dissociate further. So you have to know your polyatomic ions, and when you write them in aqueous solution, you don't break them up further. The other thing you don't do, which I see students make this mistake a lot, if you have magnesium chloride, solid, and you do the same thing, that dissociates into magnesium 2+ ions in aqueous solution, and what? Some students will write that it dissociates into Cl2, because I taught you a song a long time ago that makes you think that if it ends in GEN or INE, it combines in nature diatomically. And that's true if that's how it exists in nature, right? But this is not how it exists in nature. Here it is in aqueous solution. It's not Cl2. These are 2 chloride ions. Right? This is no different from what I did up above in red with the 2 nitrate ions. This just happens to be chloride ions. So please do not make that mistake. And I plead with students every semester, but there's still those who will make that mistake. Right? It's not a gas. You have ions in solution. All right, so electrolyte simply means we have ions in solution. And there are things that will dissolve in water when you make your sweet tea. Once again, all right, you put sugar and it dissolves in water, but sugar, in this case, I'm going to use an example, not sucrose, but I'll use glucose. Glucose is also a sugar, and glucose solid will dissolve. Here it is in aqueous solution, but when it dissolves, it does not dissociate further into ions. This is a covalent molecule. It does not dissociate further. So even though it dissolves, it doesn't form charges in solution. So this is what we call a non-electrolyte. Okay. Here we can even say we've got a solid sugar cube here. Again, even though the sugar cube that we enjoy is sucrose, not glucose. And you put that in solution and it will completely dissolve. But when it does, it's just individual molecules of glucose that are now solvated by the water molecules in a similar way to what I showed you about the sodium and the chloride ions. But there's other interactions going on there that you'll learn about in second semester. All right, so that's the simple definition of an electrolyte and a non-electrolyte, right? They both dissolve, but only one dissociates further. We then have other terms, strong and weak electrolytes. And these are perhaps not the best terms to use for what they're actually describing. Because when you think of a strong electrolyte, it's strength. It has nothing to do with the strength of it. All it refers to is the degree of dissociation. The example I showed you above for sodium chloride or magnesium sulfate or magnesium chloride, these are strong electrolytes in the sense that they dissociate 100%. So we have a solid arrow that goes from the left to the right. This reaction goes completely. Sodium chloride will completely dissociate into sodium ions and chloride ions. There are weak electrolytes that only partially dissociate. So that's why we call them weak. So here, just as example, NaCl, this goes to 100% sodium ions and chloride ions. A weak electrolyte, here's one favorite example. This is acetic acid. Acetic acid is a weak acid. And actually, I shouldn't say acid. Well, it's acetic acid. It's a weak electrolyte. As you'll see in a moment, acids are also electrolytes because they form charged ions in solution. But acetic acid does not dissociate completely. It does this double-headed arrow. What do we call that again when we have the double-headed arrow? I told you the last time. Equilibrium. All right. These are reactions that don't go to completion. This will dissociate only partially into the acetate ion. This is another polyatomic ion. In fact, your table of polyatomic ions has the acetate ion on there. So we may start using this in some examples. The acetate ion, and it has a hydrogen ion. But these are in equilibrium. The reaction does not go to completion. Equilibrium is something that you'll study a lot in second semester. The reaction doesn't go to completion. So in fact, when things are at equilibrium and they're not changing anymore, you have both reactants and products are still present. It doesn't go to completion the way we've been talking about for these other things. All right, so that's the difference between strong and weak. Here's just a visual example. If you take this little circuit here, all right, we want to use the solution to connect our circuit and see if we can light the light bulb. Well, if we put our circuit in just H2O, even though, well, it's H2O, it's liquid H2O, there's not much going on there to conduct electricity. So you don't see the light bulb go off. If we put some sodium chloride in there though, that's a strong electrolyte. So that's going to dissociate completely. It's a strong electrolyte and it's in aqueous solution. So it dissociates completely. We have charged ions in solution and the light bulb goes off. Let's light that guy up. All right, the light bulb goes off. But if we take the same sodium chloride, but have this as a solid, whoops. If we have it as a solid, it's not an aqueous solution. It's still a strong electrolyte, but that doesn't matter if it's not an aqueous solution. So you don't have ions, the light bulb doesn't go off. Ethanol is another example of a weak electrolyte. I won't explain that one. Here's acetic acid on the right-hand side. Actually, ethanol isn't even a weak electrolyte. Let's just not talk about ethanol. Let's just go right over to acetic acid. Acetic acid is a weak electrolyte, and here it is in aqueous solution. So if we had the same molarity of acetic acid as we have of NaCl, for that same molarity of electrolyte, because it's weak, you don't have as many ions in solution. So it only lights up the light bulb, but just a little bit here, not very much. It's pretty weak. Right, and that's if we have, this is assuming the same molarity. Okay, so it just gives you a visual idea of what we mean by strong and weak. Yes, there's a question.
So the equation with the polyatomic ion.
Oh, that's a great question. Let me address that to everybody. So the question was, so if you have a polyatomic ion, like in this magnesium sulfate example, right? I told you that, well, when it's a polyatomic ion, it doesn't dissociate further. So doesn't that make it a weak electrolyte? And the answer is no. It's still a strong electrolyte because the ion is, in this case, a polyatomic ion. The polyatomic ion never dissociates. That's a covalently bonded molecule that happens to be an ion because of the difference in electrons versus protons. But it's already dissociated into its ion. It just doesn't dissociate further. So what's strong or weak is the magnesium sulfate that it came from. That dissociates 100%, so it's a strong electrolyte. But the polyatomic ions never dissociate. They are molecules. Did that answer your question? Yeah, that's a really good distinction though. All right, so as I mentioned, we go into much more detail about acids and bases in Gen Chem 2, but it is introduced in this chapter in the context of them being electrolytes. So acids and bases are also electrolytes. And as such, we can have strong and weak. So we have strong bases, strong acids, and we have weak acids and bases. As I showed you already in the example, acetic acid is an example of a weak acid. But let's talk a little bit more about acids and bases. And there's a couple of different theories about acids and bases. We're just going to stay focused mostly on this Bronsted-Lowry theory of acids and bases, which defines an acid as a compound that when it's in aqueous solution, it donates a hydrogen ion to the solution. Good. That's for both of these. The definition of a base is going to be a compound that when it's in aqueous solution, it accepts a hydrogen ion. Now, there's actually a real lot of important chemical reactions, especially important for life, that are dependent on acid-base chemistry. So again, I'm just exposing you to it a little bit in this context. Now, this hydrogen ion, though, let me talk about that real briefly, and this will be a bit of a review for you, right? If I draw this symbol for you, remember how to interpret those, right? The H, we know, stands for hydrogen. And what does that one in the lower left-hand corner stand for? Who remembers? It's not the atomic mass. We call it the atomic number. And what does it stand for? Number of protons. That's right. Atomic number. Oh gosh, let's write neater than that. Atomic number is right here. That's the number of protons. So how many protons do we have in the hydrogen atom? We have one. So this is one proton. Now, what's the number in the upper left? That's the mass number. What does that tell you? The number of what? Neutrons plus protons. That's right. This is the number of neutrons plus protons. So if the mass number, if I'm telling you the mass number is 1, how many neutrons do we have? Do we have 1 or do we have 0? We have 0 neutrons because the mass number is 1. And if it's hydrogen, it's got to have 1 proton, right? If it had 1 neutron, then the mass number would be 2, right? This has 0 neutrons. If it's hydrogen, it's got to have 1 proton. Whether or not I put that 1 for the atomic number, you should know that, right? So if I now tell you that this is a neutral species, if I put a 0 up there, this is a neutral atom, how many electrons do we have? Is it 0 or is it 1? It's 1, right? Because it's neutral and the electrons have the negative charge and the protons have the positive charge. So there you go. That's the neutral atom. Let's call this the hydrogen atom. Now, when I showed you that example for acetic acid, the dissociation into its ions, it formed the acetate ion and the hydrogen ion. That's what we have here. And of course, we know how to name this. This is the hydrogen ion on the right. But let's put in our same atomic number and same mass number. How many protons? 1. How many neutrons? 0. How many electrons? 0, because now the net charge is 1 plus. So we've lost that electron. There's 0 electrons here. Okay, so the hydrogen ion by name is actually what? It's an ion, but what else is it? What else could you call this? A rose? A rose by any other name is still a rose. A hydrogen ion by any other name? It's a proton, folks. That's all it is. Look, it's 1 proton. There's nothing else there. Okay? The same protons we were talking about back in chapter 2. When you have a hydrogen ion like this, it's also a proton. And so we oftentimes will call these protons. So a Bronsted-Lowry acid will donate a proton to solution, and a Bronsted-Lowry base will accept a proton to solution. These words are interchangeable. And to emphasize that fact, I'm probably going to try to use both terms when I describe acids and bases to you in the next lecture or two. So I've already showed you some examples of an acid, right? We had a acetic acid on top. Here's another one. Here's hydrochloric acid. You've used that one in lab a lot. Hydrochloric acid happens to be a strong acid. Now in this class, I'm not going to expect you to know which one is strong and which one is weak just by looking at it. I will tell you if it's strong or if it's weak, okay? Hydrochloric acid, though, is a strong acid, so I would write it this way. Here's hydrochloric acid in aqueous solution. Well, that's going to dissociate now completely. It's not at equilibrium. It dissociates completely into its component ions, the hydrogen ion and the chloride ion. And these are both in aqueous solution. If I showed you an example of a base, just by way of example, here's a Bronsted-Lowry base. Ammonia acts as a Bronsted-Lowry base. When you have ammonia in aqueous solution, it will accept a proton from the solution. It looks like this. In fact, to show you, I need to put a water molecule in here. Okay, so here's your liquid water, and this turns out it's a weak base. So I'm going to put this is in equilibrium. The ammonia molecule is going to pick up a proton now, a hydrogen ion from the solution. So what's that going to look like? What is it going to be? NH, how many hydrogens now? 4. But what it acquired was an H plus. So no more electrons came along with it. So this now has a positive charge. You've seen this before. This is the ammonium ion. This is also a polyatomic ion. And you've seen this on your table of polyatomic ions. Now what's left over here is OH minus in aqueous solution to balance our equation. Okay? And let's just see what's going on here in this solution now. Right? The ammonia accepted a proton from the solution. And where did that proton come from? You can see from this balanced equation. Where did it come from? It came from the water. The water is donating that hydrogen ion to the solution, and the ammonia picks it up. What's left over then when the water donates a proton is it has the OH minus, that's what's left, the hydroxide ion, which is another polyatomic ion, which you're familiar with. Now, it's interesting to point out, though, when we have protons in solution like this in acid-base chemistry, protons themselves don't exist as protons in aqueous solution. When you have protons in aqueous solution, they actually combine with water molecules to form this. This is called the hydronium ion, H3O+. That's another polyatomic ion that you've seen in your table of polyatomic ions. This is an aqueous solution. It's no longer liquid water. But this is how protons actually exist in aqueous solution. So for that example of hydrochloric acid that I showed you up above, this one here, whoops, this one here, all right, let's take a look at that again. I've written it down below, but what's really happening, I have to show you in the context of H2O, all right? If I put a molecule of H2O on this side, then we have the hydronium ion on this side. Really what we're doing here in the context of water, because this proton, all right, here's H2O. Let's add that H2O over here, okay? These come together to form the hydronium ion, as I just explained. So the real balanced equation is down here. If we want to express the hydrogen ion as it really exists in solution, which is the hydronium ion. But the simple reaction for that is written right here. And notice what's happening. How is water behaving in this reaction that I just circled in red? Is water behaving as a base or as an acid? It's a base, because now water is accepting. Water accepts the proton from solution. So that's called a base. Well, up above, what was water doing here? What was water doing here? It was donating a proton to the solution. So here, water donates a proton. So it's an acid. So in one context, water's behaving as an acid. And then in another context, water's behaving as a base. It can do both things. Water is a very magical molecule. It's no wonder we need it for life. We have a special word for this, something that can behave both as an acid and a base. That's called amphoteric. Behaves both as an acid or a base. Of course, that depends on the situation. There are other molecules that can do this too, amphoteric molecules, but water is the big one, and it's a great example for this. Okay, so I told you I'm not going to have you learn how to tell by just looking at it whether an acid or a base is strong or weak. In fact, let's just talk about acids for this discussion. If we needed to use it in a problem, I would tell you whether it was strong or weak and expect you to understand what those strong and weak terms mean to figure out what to do with the question. But let me just show you some of these, because honestly, to remember which are the strong acids, it's really easy, because there's really only a handful of acids that we classify as being strong acids, or in this case, strong electrolytes. I already told you or showed you some of them, HCl, right? In fact, HCl, HBr, and HI, these are all going to be strong electrolytes. This is hydrochloric acid. This is hydrobromic acid. This is hydroiodic acid. You might just remember these as the acids of halogens that are all strong. Although, if you want to think of it that way, just be careful because hydrofluoric acid, HF, that's a weak acid. I probably won't go into the distinction of why that one's weak and the other ones are strong. Although if you're interested, I invite you to come by office hours. That's really more of a subject for Gen Chem 2. So I'll just put in parentheses here, HF is weak. But the other strong acids that you're familiar with already are these two. You use these in lab. This is nitric acid, and this is sulfuric acid. Those are also strong, okay? So they all go 100%. But what I want you to remember is that if I give you an acid and I tell you it's a strong acid, that means that this dissociates 100% into, in this case, hydrogen ions and the nitrate polyatomic ion. For bases, for this class, let's just assume that if it's a metal hydroxide, it's going to be a strong base. Most metal hydroxides that come from group 1 and group 2 metals will be strong bases. So this is group 1 or group 2 metal hydroxides. So for example, NaOH, and you've used that one in lab, right? That one goes 100% to its component ions, sodium ions in aqueous solution and hydroxide ions in aqueous solution. You got to know your polyatomic ions. That's why we stress it in lab and I stress it in lecture. That does not dissociate further into O2 minus and H plus. It stays together as a polyatomic ion. That's how it's most stable in solution. And you just know that by the fact that we classify this as a polyatomic ion. Barium hydroxide, you take a look, just like we did before with the calcium nitrate example I showed you earlier in lecture. This is a strong electrolyte, but when it dissociates into 1 part barium 2 plus cations and 2 parts hydroxide ions. You got to pay attention to the stoichiometry, both of the cation anion pair, as well as your coefficients in a balanced equation. How do you know the barium is a 2 plus? There's 2 ways. One is you can remember your polyatomic ions and you know that hydroxide is 1 minus, and you see that it's given to you as Ba and then OH in parentheses 2. So that tells you you've got 2 hydroxide ions. Each one has a 1 minus charge. So there's overall 2 minus charges. For this to be neutral, barium has to be 2 plus. Of course, there's an easier way. You look at the periodic table, barium is in group 2, and you know from earlier in the semester how to interpret that. When it forms an ion, what's the charge going to be? Being in group 2, it's going to lose 2 electrons to become most stable, isoelectronic with its nearest noble gas configuration, right? All of this should be coming back to you as good review. And those are the strongs, at least in Gen Chem 1, those are the strongs I want you to be familiar with. Pretty much everything else is going to be weak. But let me show you a few more examples of weak, okay? And just to remind you, definition-wise, weak means that only a small percent dissociates. Remember, it's all the degree of dissociation. So I already showed you for acetic acid, but let me just be complete and remind you of this. Because only a small percent dissociates, that means we end up with an equilibrium. So I'm going to draw that with the double-headed arrow. And here are the components that it dissociates into. Hydrogen ions plus the acetate ions, CH3COO minus. Now remember, as I just told you a slide ago, in solution, it's not really a proton. It's not really a hydrogen ion. That's actually a hydronium ion. But if I were to put H3O plus on there, to balance the equation, I would need to show you that there's a water molecule on the reactant side as well. So just for simplicity, I'm showing it to you this way. But you should remember that if every time you see this in solution, it's really the hydronium ion in aqueous solution. All right, this is what we call, by the way, a monoprotic acid. When it's in solution, it donates 1 proton to solution. For every mole that's in solution, it donates 1 mole of hydrogen ions, or up to 1 mole, because right now it's at equilibrium, okay? But it only has 1 proton total per molecule to give to the solution. So that's what we call monoproduct. As opposed to diproduct, right? It can donate 2 protons to solution. Here's carbonic acid. Carbonic acid is a diproduct acid. It's also a weak acid. So it's going to donate 2 protons to solution, but it does them sequentially, okay? The first proton is lost. Here it is. And what's left over? Well, that's going to be HCO3 minus in aqueous solution. You may recognize that as yet another polyatomic ion that we use in Gen Chem lab. Anyone recognize what it is and what it's called? What? It's, say it louder. This is the bicarbonate ion. It's a polyatomic ion. You used it probably this week. You used it last week. Remember sodium bicarbonate, right? It's also called hydrogen carbonate, formally. But just like we don't go around calling water dihydrogen monoxide, we call this the bicarbonate ion. But there's another proton that can be given off. There's another reaction here. This is a case where a polyatomic ion can still dissociate further, but it's a very, very, very weak dissociation. So for Gen Chem 1, we pretty much don't pay much attention to it, but there is another dissociation event here where we can donate 1 more proton to aqueous solution. And what's left over then? What do we have? CO3. What's the charge on that now? It's 2 minus now. Anyone recognize that? This is the carbonate ion. Just like we used before, like if I gave you sodium carbonate, right, it would be Na2CO3, right? Or magnesium carbonate. Have we used things like this in lab before? Surely I've given you an example like that. I think I have. Okay. So these are all weak events, right? As shown by the double-headed arrow. Let's say this is weak, and I'll say that this is even weaker. That's the trend you tend to see. And again, we would explore this in more detail in Gen Chem 2. When you have multiple events like this, the first one is stronger than the next one, and that's stronger, bless you, that's stronger than even the third one. Let me show you an example where there's 3. Oh, wait, I don't have that. I took it off of here. All right, let me show you a different example instead. Yes, question. Yes, anytime I would write H plus, it's really H3O plus. But it's fine for us to write it this way, as long as you know what we're talking about. For me to formally put H3O plus there, I would need to balance it. And I don't like showing you things that aren't balanced. But yes, these are synonymous. Let me emphasize that. Treat these as the same thing. All right, so let's end with this example here. Sulfuric acid, which I already just defined up above, is a strong acid. And it is a strong acid. The first dissociation is what's strong, losing that first proton. This is 100%. And when we lose that first proton, we get the hydrogen ion or the hydronium ion in aqueous solution, plus whatever's left over. That's HSO4 minus. in aqueous solution. There's no other name for this one. There's no common name for it. This is the hydrogen sulfate ion. So it's a strong acid. Again, sulfuric acid, we think of it as hurting you, right? But it doesn't hurt you because it's a strong acid. Because you can get just as hurt by carbonic acid as you can by sulfuric acid. It all depends on the concentration of the acid. Strong and weak only talk about the extent of dissociation. It has nothing to do with how concentrated it is. That's what can hurt you. That's more of a subtle point. Let me finish by finishing this idea. We do get another loss of a proton here, H plus into aqueous solution, and what's left over? SO4, what's the charge on that? 2 minus. And you all will probably recognize that as another polyatomic ion. This is the sulfate ion. We've used this plenty. Okay? But it's still, this is a strong acid. This is just the second loss. This is very, very weak. It's much, much, much less. Oops, I should do it this way. It's much, much less than 100%. It's almost negligible, okay? But these are both examples of diproduct acids. There's other examples. There's some that phosphoric acid. Okay, so this is a good place to stop. And on Monday,